So our keynote speaker today is Dr. Dina Katabi, a professor in the Department of Electrical Engineering and Computer Science here at MIT. Dr. Katabi is a member of the Computer Science and Artificial Intelligence Laboratory and the director of MIT's Center for Wireless Networks and Mobile Computing. Dr. Katabi's research focuses on computer networks, wireless systems, network security, and distributed resource management. She received her PhD and MS from MIT in 2003 and 1999, and her Bachelor of Science from Damascus University in 1995. Dr. Katabi won a MacArthur Fellowship, the Genius Award, in 2013. She also received the ACM Grace Murray Hopper Award in 2013, a Faculty Research Innovation Fellowship in 2011, the IEEE William R. Bennett Prize in 2009, a Sloan Fellowship in 2006, the NBX Career Development Chair in 2006, and an NSF Career Award in 2005. Wow, that's a lot of awards. Her doctoral dissertation won an ACM Honorable Mention Award and a Sprouse Award for Academic Excellence. She also received multiple Best Paper Awards from ACM, SIGCOMM, and USENIX NSDI. Her work on the sparse Fourier transform was named one of the 10 breakthroughs of the year by Technology Review magazine. Please join me in welcoming Dr. Dina Katabi, who will speak to us about visions of the wireless future, insights into emerging technologies, and share with us some of her recent investigations.
Hello, everyone. My name is Dina Katabi, and I'm really happy to be here today to talk to you and share with you this very nice event promoting math among girls. What I'm going to tell you today about is wireless systems and wireless networks. I work on wireless systems, and this is like the typical thing that we do has to do with Wi-Fi, with cellular networks. But also I'm going to show you that we do many other things that you wouldn't probably imagine that it's possible to do them with wireless signals. So I'm going to go over a few systems that we developed recently, and I'm going to jump from one topic to another to show you what we could possibly do with wireless signals. So let me start. The first system that I want to tell you about is called Megaminer, or how you can get 10 times higher data rates for your cell phone or your Wi-Fi connection. So I'm not sure, maybe most of you know about that we are facing a wireless crunch. What does that mean? So wireless system, wireless medium is a shared medium. It's like speaking in a room. So when your cell phone, for example, transmits, it's like speaking in a room. It cannot, this is a shared medium. We cannot all speak at the same time. This is why you get one speaker after another. The same way happens with wireless medium. It's a shared medium, so one transmitter has to go after the other transmitter. Otherwise, you get a chaos. And this is why we say that the spectrum is limited resource. In fact, it's so limited that we are running out of spectrum. So the FCC, which is the organization in the US that handles the allocation of wireless spectrum, has told us that we are running out of spectrum in the US. Actually, we started running out of spectrum in 2013. So you can see the red part of the graph goes under zero. So we are in shortage of spectrum for all the things that we want to do. I'm not sure whether you guys remember the Steve Jobs talk during iPhone 4 demo. How many people have seen that talk? Okay, none of the younger people, I see. But you guys know the iPhone 4, okay? Beyond the iPhone 6, before the iPhone 6 was the iPhone 4. So that was even 4 or 5 years ago, and I'm sure you know Steve Jobs. Do you? Steve Jobs, okay. So Steve Jobs stood there and he wanted to demo this new thing at the time, the iPhone 4, and this is an amazing thing that can connect us, and he wanted to show a Wi-Fi demo on the iPhone 4. What happened? What happened for the guys who remember the talk? It didn't work. And you know why it didn't work? Because wireless is a shared medium, and there were so many people in the audience that were using Wi-Fi on their laptops or their MiFi stations, and all of them were sharing that one resource, the spectrum, and Steve Jobs couldn't demo the iPhone 4. So what did he tell the audience at the time? He told them to turn off their laptops, turn off their MiFi stations, put them on the floor if you want to see the demos, please. So of course, this is not a solution that we want for our future networks. We don't want to turn off our laptops. We want more data rates for the same spectrum. And this is exactly the problem that we try to solve with this system called Megaminer to give you higher data rates, higher speed for your data using the same shared spectrum. So let me start by telling you at a very, very high level how Wi-Fi works. And this is also, to some extent, applies to any wireless networks. So if you have a Wi-Fi network, and these are what we call the Wi-Fi routers or access points, and each one of them wants to talk to its user. Now, you cannot make all of these transmitters transmit at the same time in the same frequency band, in the same spectrum band, because if you do, they will just interfere. It would be like so many people shouting and yelling at the same time in the same room. Nobody can hear anything. And this is exactly the problem that this new system called Megaminer solves. So these Megaminer routers are smart. They are going to encode the data in a particular way to eliminate that problem, so that when they transmit, all the user can get their data, although we are transmitting at the same time in the same spectrum band or spectrum channel. Now, of course, you cannot eliminate interference. This is physics. And just like this is the nature of life, wireless signals share the medium. When you have multiple people shouting, they're going to interfere. But you can control the interference. And indeed, you can control the interference with math. So what these smart access points are doing, they are ensuring at each user the interference, which is the data intended for the other users, will sum up to 0. And only the data intended for this user will survive. So here, for example, you see at user 1 has an antenna. And at user 1's antenna, the data intended for user 2 and 3 will sum up to 0, and only the data intended for user 1 will survive. And therefore, for user 1, it's as if the other guys don't exist, and he can use the whole spectrum. Now, of course, I'm showing this as you sum up the data, D1 and D2, but this is much more complex than that, because that data is a wireless wave or an electromagnetic transmission, so you have to be careful about what does it mean to sum up two electromagnetic waves and make them cancel out at a particular antenna. But if you can do this, then you can apply it to user 1. You can apply the same thing to user 2 and 3, and have the interference at user 2 and 3 will sum up to 0, and only the data they are interested in will survive. And with this, you can make many of us transmit and receive at the same time in the same spectrum band. So imagine, like in this room, we can all shout to our intended receiver or our audience, and everyone will get our data or the information that we want, despite the fact of all shouting that's happening in the environment. So this is exactly what the system can do. I'm gonna go skip all of the details, technical details, but let me show you that actually it does work. So what we did here, you see 1, 2, 3, up to 10. These are transmitters deployed here in the MIT Computer Science Lab. And what we did, we made them transmit together using this Megaminer system. And let me show you the results. So on the x-axis is the number of transmitters on the same unit of spectrum. On the y-axis is the throughput that you can get from these transmitters. And as you can see, if you use today's system, because we have to rotate, either I speak or you or the other person, the red line is just straight. You can add more transmitters, but you won't get higher throughput for your network. While the blue line, which is this new system, gives you about 10 times improvement in the data rates for your cell phones, for your Wi-Fi receivers. So hopefully, And once the system is deployed by Verizon or AT&T, your data bill will go down and will charge you less. So I'm going to move now to a new system to show you even what we can do beyond communications with wireless signals. But I want to ask you guys, do you have any question about this? And you have to shout if you want me to hear your question. Go ahead.
My question is why the x-axis, the maximum is 10, not 100?
Excellent. So the question is, why did we stop at 10 here? Maybe if we have more than 10 transmitters transmitting together, we can get more than 10 times improvement in the throughput. And the reason for that is that we are cheap academics at MIT. So faculty have only limited resources, so we had only 10 transmitters to work with. Of course, if you add more, you can show more improvement in throughput. Can we move? Yeah, you can move as long as you are moving within, like if you are like walking with your laptop or cell phone, that's fine. If you are in cars or high-speed trains, then things get much nastier. But yeah, if you are moving like I'm moving now here, or as just walking, that's fine. Okay, so let me move on to something that you might not expect that we can do with wireless signals, which is to track your movements. So imagine, for example, that we can track how you are moving just using your cell phones by tracking the signal coming out of your cell phone. So for example, when you are in Macy's or in the mall and you are looking at some dress or some stuff, you will get a coupon because we discover exactly what you are looking at and where you are. Basically, everyone wants to be able to track people indoors. GPS has changed our life, but GPS works only outdoors. What if we can have navigation and localization indoors? And this is you can do with wireless signals. And in fact, if you can do very accurate localization, then you can imagine putting wireless circuits on gloves, and then moving your hands and start to get virtual screens in the air, like Tom Cruise in Minority Report. So you can just scroll through windows or zoom out or zoom in and do all that stuff just in the air. But to do that, you need to be able to localize objects in our body very accurately. So let's see what we can do. Now, the biggest problem when you are trying to localize using wireless signals is that they bounce off everything in the environment. I transmit a wireless signal, it bounces off the floor, off the ceiling, off the furniture, of our bodies. And therefore, you cannot just say, oh, the wireless signal is coming this way. It means that the sender is this direction because of all the bouncing effect. So what can you do? I mean, you do what every academic does, is to say, let us change the problem to an opportunity. So what if we can use that bouncing effect as a signature of space? So I can look at the bouncing effect and decide, because this is the exact bouncing I'm seeing, the guy is here. So let me show you like visually an example. So here there is this blue source, and when it transmits, the signal arrives to the receiver along two paths. The first path is 35 degrees, and the other path is 140 degrees. Now, this graph at the bottom that I'm plotting to you is the power of the signal as a function of the direction. So if I plot the power of the signal from here, from here, from here, I will see the power of the signal from all the directions. And as I said, I will see particularly that the power peaks at 35 degrees and at 140 degrees, because these are the major bouncing effects that this source has encountered. Now let me show you this green source that is close by. You see that this profile of how things are jumping up and down is actually very similar, because the two of them are very close to each other. So what we went ahead and did is to try to use that profile of how the signal bounces around to localize these sources. And we can actually do it to localize sources to within about 10 centimeters. And what we did is, of course, we can localize cell phones, and that's easy, but what we wanted to localize is RFIDs. So RFIDs are stickers who knows RFIDs in the audience? Okay, not many people. So RFIDs are very nice things. They are battery-free stickers. The property of this RFID is that when you shine a wireless signal on it, it reflects the signal, but it also reflects its own ID. So this guy, for example, is going, when I shine wireless signal, is going to reflect the signal and say, oh, I am RFID number 5, or I am RFID number 20, and so on. Now, another thing that is really interesting about these RFIDs is that each one of them costs about a few cents. So with $20, probably I can tag $20, maybe $40, there are many of you guys here. I can tag all of your credit card, your keychains, all of the objects in your pocket. And I probably can use another $20 to tag all the furniture around, and then I can localize you with respect to the furniture, and if you lose your credit card, for example, we can localize it and identify where it is. Now, the experiment that I'm going to show you that we did with these localization is a particular experiment that many of the people in the industry are interested in, which is called to eliminate the customer checkout line. So, for example, if you can put RFID stickers like the one in my hand on all of the objects in the store, and you can put some stickers on the basket of each customer, and if you can localize these objects within the basket, then forget about these long checkout lines. You can immediately detect when a customer takes an object and put it in her basket, and charge them when they exit the place because you are tracking their motion. There'll be no waiting line. Imagine, you guys, how many times you waited in line. All of that will be eliminated. Okay, so let me show you what we can do. So here's a customer. She's interested in buying the red Pringles, and what you can see here is that we have RFIDs on her basket, on the shelf, and on the object in the store. Particularly, she's interested in the red Pringles. So now let me show you these graphs, which are this bouncing effect that I was just talking about. And you can see the bouncing effect for the basket in orange, and the Pringles in red, and the shelf in black. And in fact, our algorithm, and you also visually can immediately recognize that the red graph is closer to the black graph, so the Pringles are still on the shelf. Now let me show you what happens when this customer takes the Pringles and put them in her basket. Now, of course, the Pringles have moved from the shelf to the basket, so the bouncing effect is very different now in the basket. And here, the algorithm discovered the new bouncing effect, and you can see very clearly that now the red Pringles are much closer to the bouncing effect of the basket. So you can immediately tell when somebody grabs an object and put it in their basket. Now with this, not only you can eliminate all customer checkout lines, but again, imagine putting that sticker on your credit cards, on your favorite toy, on your cell phone, on your laptop, and now putting some of them on the object inside your house, and you'll never lose your credit card anymore because you can localize it depending on which object is the closest to, like it's under the chair or under the table. Not only this, also, I showed you at the beginning that if we want to do this Tom Cruise thing in Minority Report, where we want to have these virtual screens in the air where we can scroll through a window or zoom out or zoom in or move windows. In fact, we want to do more than this. I want to be able to write in the air and use that as a virtual tablet, so that I can recognize, I can go to Starbucks and write in the air latte, and that will be my order. Do you think I can do that? What do you guys think? So we did exactly this, and because we can localize these RFID very accurately, so here what you see is my student put an RFID on a finger splint, and she wrote in the air the word help. That was before the conference deadline, and she was working really hard. So she was trying to get some help from the other students. So we are not that far, really, from getting these virtual screens in the air. And now you guys could take an RFID and update my screen here from where you are sitting. But let me show you something even more exciting and surprising, probably, that we can do. In particular, what do you think? Can we get X-ray vision on our handheld devices using wireless signals? Like, for example, can I take my cell phone and shine a wireless signal on this wall and start on the screen seeing how people are moving behind the wall? Can we? No? Yes? No? Who says no? Sorry, what?
If the wall is metal, you can't.
If there's no metal, then we can. If the wall is metallic, wireless signal will not get through it. So forget even about being able to get your cellular signal. That's not going to work. But the vast majority of walls don't have that much metal in them. So can we get it? So I can't tell you that we can get it. We cannot see the people. We cannot see their hair. We cannot see their fingers. But really, we can track their movements very accurately. We can discover exactly how they are moving in the environment behind the wall without them helping us at all doing that. So let me show you this video. So here's our wireless device. It is in a different room. It's behind the wall in the adjacent office. And what you see here, this is the screen of the device. This is the screen of the device in the other room. And this red dot is where the device thinks this person is at this current point in time. Now, the spiral on the floor is just for visual help so that you can map what you see in the video with the screen in the device and the red dot. And all that we are doing here, we are shining a wireless signal through the wall and receiving its reflection. And based on those minute reflections of the person's body and of all the objects in the environment, we are going to track how he's moving. Okay, so look at the red dot and see whether it tracks the person. So here he's moving. And you can see the red dot is tracking him pretty accurately. He doesn't have any wireless device on him. He doesn't have a cell phone. He doesn't have any device that is helping us in doing that. We are purely doing it based on the reflection of the signal of his body. What? No, there is no sticker on him. And in fact, we can track even his hand motion, not just his whole body. So he can point, for example, at the lamp. We can discover where he pointed and turn off the lamp. He can turn off the screen by pointing at it. And say, for example, you forget the lights on in another room and you left the room. You can turn the lights off just simply by pointing at them. Okay, so really wireless signals and wireless systems are taking us beyond what we traditionally imagine. We typically think about, okay, doing wireless communications basically with wireless signals. But there are so many things that we can discover with these wireless signals. Now, in all of these videos that I showed you where we have this form of X-ray vision, we are tracking a human that is moving. Even the hand has to be moving. So now, let me ask you, you guys are not moving. You are sitting in your chair. Can we discover where you are sitting and track you without any movement? Possible. Everything, actually, this is the correct answer for any question. Everything, otherwise, I wouldn't ask the question if we cannot do it. But the reason is because something is moving in you. you are breathing, so your chest is moving, your heart is beating. So in fact, we can follow and track your breathing and your heart rate without any contact with your body from even a different room and discover how you are breathing and discover your heart rate. So let me show you this picture. Not picture, actually, it's a video. So for people who have babies in their homes, let me stop it for a second. This is a baby monitor, where you are seeing here, and the baby is sleeping, so you cannot tell anything beyond that. You see the image, and he's sleeping. So I'm going to play the video for you. What? Okay, so now the video is playing, and you can see time is moving up there. It's 33, 34, but the baby is sleeping. So what we did is we augmented the baby monitor with our ability to track breathing and heart rate. And very soon you're going to see this is the inhale and exhale of the baby chest. This is his inhale and exhale motion. And you can see here his heart beating. So actually, let me stop the video. So this is inhale, exhale, and this is his heartbeat. And babies have higher heartbeats than adults, so his heart is beating at the proper rate. So I'm going to end my talk here and take any question from you guys. But what I hope that I convey to you is that the world is so exciting, and there are so many cool things that you can do with your knowledge. And all these cool things, underneath them, there is a huge, beautiful collection of different mathematical tools that we use to do this, without which we definitely will not be able to do any of this. Thank you very much. Do I have time for any questions? Okay, so any questions, guys? Yes? You have to shout. So for tracking heart rate and tracking people behind walls is about 10 meters. And the real limitation is coming from the FCC, which is the organization that puts a cap on how much power each one of us as consumers can transmit. So it's about 10 meters. Anything else? How much what? Computing, not much. In fact, the demos that I showed you are real-time demos. And if you guys come to our lab, you can sit there and watch your breathing. You can hold your breath and see how the breathing signal stops. And you can release your breath and see how the inhale-exhale motion is there. So all can happen in real time, not much computation. Yes? I see. You're saying, what if the person is buried under sand or under snow? So actually, we can do that. It depends on how much attenuation the material has. So snow has less attenuation than sand. Sand, it depends on what exactly the sand that you are talking about. But you can envision using these kind of technologies for a search and rescue mission. Like, for example, when you have a disaster and you don't want to send the firefighters or the rescue team inside before they check where the person is and can locate him. So I give this talk to our MIT undergraduate in one of our largest undergraduate system classes. And after I give the presentation, one of the undergraduate students came to me and said, "Oh, does it work actually in dorms?" And I said, "What do you mean?" It's like, if I take this device and put it in the dorm, can I actually start tracking other people on what they are doing? And it's like, it's not recommended, really, that you do that. Okay, so let me finish my presentation, and thank you guys very much for being here today, and thank you for the great work that you all did. Thanks.